April 10, 2026. 7:53 p.m. Eastern Time. The Orion capsule, carrying Wiseman, Glover, Koch, and Hansen, slams into the atmospheric interface. This isn't just a standard re-entry. It is a moment of extreme technical peril. NASA's Amit Kshatriya and Howard, who are watching the telemetry, drop to zero. For the next 6 minutes, the crew is encased in a plasma sheath, a literal cage of ionized gas that blocks all communication. But the real fear isn't the heat, it's the Avcoat. Engineers know that beneath the glowing surface, the material may be exploding. This is the story of how NASA chose to fly a flawed shield, relying on a desperate mathematical workaround to bring 4 humans home. When Artemis I splashed down in 2022, it looked like a success. But the post-flight inspection revealed over 100 locations of unexpected char loss. Howard, the Orion program manager, convened a multidisciplinary team to find the root cause. Using ArcJet facilities at NASA Ames and Marshall Space Flight Center, researchers like Ronnie Bacuse and Terry Abel discovered a critical flaw in the modern Avcoat block configuration. Unlike the Apollo-era honeycomb, the Artemis blocks lacked permeability. During the skip re-entry, the outer char layer cooled and sealed during the skip back into space. Meanwhile, the internal layers were still undergoing pyrolysis, turning resin into gas. With no way to vent, internal pressure built up until chunks of the shield literally popped off like a cork from a bottle. By late 2024, NASA faced a nightmare. The Artemis II shield was already bonded to the titanium skeleton. Replacing it meant an 18-month delay. Retired astronaut and engineer Charles Camarda sounded the alarm, calling the decision to fly Russian roulette. He argued the physics of the cracking weren't fully modeled. However, NASA engineers, led by Amit Kshatriya, proposed a technical countermeasure. They abandoned the double-bounce skip maneuver used on Artemis I. Instead, they designed a lofted trajectory. By entering at a steeper, more direct angle, they would force the outer char layer to stay hot and permeable. It would be a hotter re-entry, but it would allow the shield to breathe and prevent the pressure buildup that caused the Artemis I craters. 7:53 p.m. The integrity hits the atmosphere. Because of the lofted profile, the crew is feeling sustained high G loads earlier than expected. The heat shield is performing its primary job, ablation. As the Avcoat burns, it carries energy away from the capsule. Researchers at NASA Ames had predicted that while this path increases peak heating, it minimizes the soak time that leads to internal gas pockets. For 13 minutes, the heat shield erodes. Inside, the temperature remains a cozy 75 degrees Fahrenheit while the outside is a 5,000 degrees Fahrenheit inferno. At 8:07 p.m., the drogues fire, then the mains. The gamble, built on the research of hundreds of engineers who looked the crew in the eye, has paid off. Artemis II proved that engineering intuition and modified trajectories can save a mission. But NASA isn't taking that risk for the moon landing. For Artemis III, the heat shield is being completely redesigned. The manufacturing process at the Machute assembly facility has been overhauled to ensure uniform permeability across all 180 blocks. No more lofted workarounds. We are going back to the moon, and this time, the shield will be as perfect as the math allows. As Victor Glover put it, space is high risk, it has to work.